Welcome to this seminar with William Pettersson, who's going to talk about kidney exchange programs and how to save lives using combinatorial optimization, I guess. So we just talked before starting the recording. William Pettersson would like to characterize himself as a mathematician who's interested in, what was it? I suggested real-world efficient communication. He suggested more broadly real-world impact. Is that correct?
Yep.
So without further ado, the floor is yours, William, please.
All right, thank you, Jacob, and thank you for inviting me and hosting me here. We did have a visit planned even last year, but of course, that's a bit hard right now. So yes, I'm going to be talking about kidney exchange programs. The title slide is up and you might realize there's a lot of names on here. So I really do want to stress that kidney exchange programs is a big field. I have worked with a lot of people in the field, so by no means have I researched or come up with all of the ideas I'm going to talk about. In fact, most of the ideas here, I'm going to be giving to begin with a rough overview of the field. So they're not going to be ideas from me. They're going to be ideas that come before me. I'm also going to point out in particular that the last so-called author on this list is called the European Network for Collaboration in Kidney Exchange Programs. So this is a cost action. So it's funded by the EU, an EU Horizon 2020 grant. So there is a lot of people hidden under there who I've also worked with as well. So this is even a cut down authors list. And even allowing for that, I'm sure I've missed people off. So I do just want to stress there's a lot of people who do work on these sorts of things. This is not the sort of field where you work by yourself. You do work in big teams. So anyway, that out of the way, let's talk about kidney exchange programs. So to start with, just briefly, I'm going to talk about kidney disease. Just for people's clarity, I will say I'm not going to be posting pictures of any medical things or anything like that. So you don't have to be worried about getting queasy or nauseous or anything. It's just going to be text in that regard. But I do have to talk about it, I guess. So kidney disease, it actually affects somewhere around 10% of the world's population. So you can easily see that there's a lot of people. For this talk in particular, I looked up the rate. So there was just over 1,000 deaths in Sweden alone in 2018 due to kidney disease. So kidney disease, it sounds like an illness that you might be able to get better from, but it's completely not. It is essentially your kidneys starting to shut down. There's a number of reasons which may cause you to have kidney disease, but I'm not going to go into too much of those. Basically, what happens is your kidneys stop working properly. And as you go through the stages of kidney disease, your kidneys will just completely shut down. So there are two treatment options that are known at the moment. One is dialysis, the other is kidney transplant. And obviously, we're going to talk about the second one. But just briefly, so what is dialysis? This is where you are actually, if a person who has kidney disease and who is on dialysis is plugged into a dialysis machine, and it does involve tubes taking people's blood into the machine, where the machine essentially replicates the effect of a kidney. This is something that, so obviously depending on how bad you have kidney disease, this could be anywhere from 3 times a week to daily, and between 3 to 8 hours each time. There is also a trade-off between these things. So if you're doing it daily, maybe you only have to do it a few hours at a time. If you're doing it 3 times a week, you might need to do it 8 hours each time. Everyone is going to have an individual sort of prescription in terms of dialysis when it comes to this sort of thing, and it's going to be changing as well as you progress. This obviously affects your quality of life. You do have to be hooked up to this machine to keep living. This is not sort of a one-off sort of thing or even a short period of time thing. And I do want to stress it's an ongoing treatment. This is not you do dialysis for 6 months and you're okay. This is for the rest of your life, you have to keep doing this sort of thing. So it has a huge effect on someone's quality of life. You have to have this machine. So you either need to be going to a hospital a few times a week, or you need to have a rather big, this is sort of filing cabinet sized machine that you sleep next to or are plugged into for a few hours a day. So going on holidays overseas can almost be completely impossible to do. So dialysis is very hard to do. Kidney transplant is a lot better in pretty much all regards. So you get a better quality of life. So in particular here, I'm going to point out that obviously there is a surgery involved when you get a kidney. Once you have been through the surgery and your body has accepted the kidney, you can go on living essentially a normal life. There are people who have run marathons after getting a transplant. So your sporting and exercise and all that sort of stuff can be completely fine and back to normal. Because it always comes up, I sort of end up mentioning it anyway. You are still going to be allowed to drink alcohol after getting a kidney transplant in general. There's no sort of hard and fast rule about that. Obviously, you do have someone else's kidney inside you. There's no guarantee it's going to last forever. So generally they'll ask people to take care of their new kidneys, but they will still be functioning the way a normal kidney would be doing. They will be filtering your blood. They will be removing the toxins. So yes, you can still drink alcohol. It says better life expectancy. I'm going to say that with regards to dialysis, obviously, it's not like getting a new kidney somehow makes your life longer, but you are likely to live a lot longer if you have a kidney transplant versus being on dialysis. And when you think about it, it's obvious, but kidney transplants are cheaper because it's a one-off operation. You do the operation and then you are okay for the next 5-10 years before maybe you might need another one. Whereas dialysis, you have to be connected to this very expensive machine many times a week for many hours at a time. You're going to need nurses and doctors involved all the time. It's very expensive. Okay, so I've explained all of this sort of thing that's going on. So obviously it seems kidney transplants is the way to go. Why do we even have dialysis? Well, the reason dialysis wins is that it's easy to create dialysis machines compared to creating a kidney. I mean, that's what a dialysis machine is, except it's just very big, right? It's a mechanical kidney. So the problem is we don't have enough donor kidneys. I'm going to point out as well, it's written down the bottom, people tend to have 2 kidneys. Obviously there are aberrations, but in general, people have 2 kidneys. It is a complete redundancy to have 2 kidneys. It is, so when people donate a kidney, they will go donate one, keep the second one. That again does not affect your life. Again, I keep having to mention, it doesn't affect your ability to have some drinks if you want. You can still do all your sport, run marathons, all of that sort of thing with just one kidney. It's completely fine. The second kidney is completely redundant. Evolutionarily, I don't know exactly why it's there, obviously, but redundancy is the best guess we have at the moment. So, okay, so we want these donor kidneys. Where do they come from? Well, there's two sort of obvious split here. We've got deceased donors and living donors. So one of the problems that sort of comes up here is deceased donors are not incredibly rare, but there is one sort of issue that we do have to deal with deceased donors, and that is that once someone dies, or once you have sort of the kidney, there is a lifetime on the kidney, like until you cannot then put it into someone else's body, until you can do the transplantation. Medically, this is called the cold isochemic time. Basically, it is time to travel for the kidney from one person to the other. And in particular, if it's a deceased donor, that time starts counting when the person has died. Because at that point, the kidney is no longer getting any blood or anything to function. It is dying by itself. So the problem here is that depending on which surgeons you ask, they're going to give you different time limits, but generally it's sort of at 12 hours or less is the time you have. Some surgeons might be happy with up to sort of 16 to 20 hours, but most won't even do that. So if you start thinking about this a bit, a deceased donor, if there's a car accident at 7 o'clock at night, you have until 7 o'clock the next morning, maybe. In that time, you need to find out who the person who died was. You need to find out, are they willing to donate a kidney? You need to talk to their family, make sure their family is still okay with it, because that can also come into it. Maybe there's going to be a will involved. Maybe there's going to be lawyers involved. Once you have that information, you need to contact the kidney registry and find out, okay, who's waiting for a kidney? Is there someone who is compatible? Are they going to be close enough? So even just physical distance. For instance, I think you guys are in Lund. If there's an accident up in Uppsala, you might not be able to get there in time to get the kidney. So it needs to be geographically close. Once you found the recipient, you need to talk to them. You need to talk to their specialist, find out if they're okay. If they're okay with it, you then need to get them into a hospital, which has an operating theater, and have them prepped for surgery. And you've got 12 hours to do all of this. So oftentimes with deceased donors, it's very hard to sort of do anything in terms of optimality here. And it's just a case of, okay, we try to find the best we can in a very short amount of time. So even though it seems like deceased donors should be able to cover all of our problems, there's so many problems with finding appropriate recipients that it's just very hard to do. The other option we have is living donors, and this is where most of the rest of the talk is going to go on with. So living donors, obviously this time restriction is something that is not anywhere near as important. If you've got a living donor, you can sort of say, okay, well, we've got an operating theater free in 2 weeks' time. Can you come in then? Yes. Okay, that's fine. We've got 2 weeks to organize everything. And even 2 weeks is a short time frame. Obviously, it's going to be months sometimes. So the planning stage is a lot more smooth though. But even if you have a willing living donor, there are more problems that come up, of course. We need this medical compatibility. And this is the idea that you can't just take anyone's kidney and put it into any other person. So most people have sort of heard of this blood groups and blood compatibility. So you've got these type O, A, B, and type A, B blood. So that is one thing that needs to be considered for medical compatibility. There's also a thing, I've written here tissue type compatibility. It's another level of this medical compatibility. There's no need to go into too many details. One thing that's always interesting to mention, though, is that things like the size, and especially for mathematicians, mentioning geometry and topology of the kidney. So size and geometry are roughly the same thing here. It's just how big is the kidney, what sort of shape is it, can we squeeze it in physically into a person? But topology, we're actually talking about how many arteries and veins are connected to the kidney. And this is something I did not know until a couple of years back, but kidneys don't always have the same number of veins or arteries. Sometimes it's one, sometimes two, sometimes three, very rarely four. And they need to match up in the appropriate way. So you can sometimes have more, I can't remember which way it is. It's either you can have more veins going in or more arteries coming out. One of the two is okay, the other one is not. But there are those sorts of considerations, and even things like the age or the health of the donor kidney. So this in particular comes down to when you have pediatric, so child-aged recipients under the age of 10. There's going to be a lot more concerns about not just the size, but also how old is the kidney, because you don't necessarily want to take a kidney from a 65-year-old and try to putting that into a 5-year-old, simply because you sort of want to try to find the best possible match for this 5-year-old. So there's lots of things that can be involved here. Okay, so at the moment we've had to find a living donor, probably because deceased donors are hard to work with, and they need to be medically compatible. But even if you know of those things, we still need to find someone who is willing to give up a kidney. So at this point, we are saying to someone, okay, hey, will you please give me one of your 2 kidneys? And that is a big thing to ask anyone already. So this is how it used to be up until sort of basically the turn of the millennium. Someone who had kidney disease either had to wait for this deceased donor waiting list, which was not quite, but almost like a lottery. It was very lucky to actually get a kidney off there. Or you had to find someone who was willing to give you a kidney. And then you had to go and have the tests and find out, can they medically give me the kidney? And if it's yes, good. But if it's a no, you sort of have to start again from the start and go, okay, well, I now have to find someone else who's willing to give me a kidney. So this is where sort of kidney exchange programs now start coming into. We can start to talk a bit about the optimization side. So just to start off with a brief example. So if we have Alice, a donor, and Bob, a recipient, I'm going to point out here as well that we try to say donor and recipient. Technically, if this was a procedure, so in this case, I've got a green arrow from Alice to Bob. This means that Alice can give a kidney to Bob. That's what the green arrow means. In this situation, there is going to be 2 surgeries. So there's going to be one surgery, which is called a nephrectomy, which is where Alice has the kidney removed from her body, and a second surgery where Bob gets the kidney inserted as transplantation. So this is actually 2 transplants going on, 2 surgeries going on for the one transplant. And in both of these surgeries, both Alice and Bob are patients. So generally we avoid using the word patient. We sort of talk about donor and a recipient. So in this case, if Alice and Bob are compatible, everything is fine. Alice donates a kidney and Bob gets the kidney, and they are both happy because they know each other and they are agreeing to this match. But if I draw a red arrow here, so now we've got Alice and Bob has talked to Alice, and Alice is happy to donate a kidney, but then they go and do the medical tests and they find out, oh, Alice is not medically compatible with Bob. I mean, before the turn of the century, before these kidney exchange programs started up, the case was, okay, Bob, you have to go find someone else now. Alice is not useful for you. But what we can do is something a little bit different. If we have another of these pairs, so in this case, I've got Alice and Bob know each other. Alice wants to give a kidney to Bob, but can't. Also, we have Charlie and Dave. Charlie and Dave know each other. Charlie wants to give a kidney to Dave, but Charlie can't because they're medically incompatible. But what if it was possible that Alice could give a kidney to Dave and Charlie could give a kidney to Bob? And this is exactly what kidney exchange programs are doing. So they're sort of allowing for this swap, this exchange of kidneys. So in this setup, it would be that Alice donates a kidney to Dave and Charlie donates a kidney to Bob. And this would happen even though Alice and Dave won't know each other. Charlie and Bob won't know each other. And indeed, in several countries, it is a necessary requirement legally that they cannot know each other in these sorts of systems. So this is what would happen. And people have one of the concerns that was first raised with these sorts of programs is, okay, well, how would Alice feel if her kidney does not actually end up going to Bob? And in every case where they've spoken to donors and recipients after the transplants have gone ahead, everyone has been happy with the outcome. Because while Alice's kidney might not have actually physically been the one that went inside Bob, Alice still knows that she donated a kidney so that Bob could receive a kidney. So, and Bob feels the same way too. So everyone still feels like, yes, it was very much the good decision, the right decision, the happy decision to make. So even though the kidneys aren't going to the person you expect, everyone is still very happy with this process. So this is the very most basic idea of a kidney exchange. I've got these lovely pictures of people, which I'm now going to get rid of, because one of the things that was sort of subtly hidden in that picture is that I talked about Alice and Bob knew each other, and Charlie and Dave knew each other. They were happy to go into this process. So in this case, sort of just a transitionary picture. Imagine them as sort of two sides of a half circle. So Alice and Bob are somehow paired together, and Alice is not going to donate a kidney arbitrarily. Alice is only willing to donate a kidney if Alice also gets a guarantee that Bob is going to receive a kidney. And the half circle, because the next image is, oh, well, there's no point in having Alice and Bob as separate entities. We can just make them one node in a directed graph. So in this case, we've got Alice and Bob up top, Charlie and Dave down bottom, and the two green arrows means that the donor of Alice and Bob, which is Alice in this case, can donate to the recipient of the Charlie-Dave pair, and vice versa. So this is now sort of starting to get into more of the optimization thing. You can sort of see we have, okay, the beginnings of a directed graph. We have some directed arrows indicating where transplants can go ahead. Seems like we want to find as many arrows as possible. A couple of things that I do want to point out here is that obviously every vertex needs to have an in and out degree of 1 when we have selected our transplants. One other thing that is not necessarily obvious until someone points it out is that, as I mentioned, every transplant involves 2 surgeries. There is the one surgery, the nephrectomy to remove the kidney, and then the transplant to actually put the kidney into the second person. So this 2 cycle that I have here, these two transplants, that would necessitate 4 surgeries. Now, in the whole world, and I think asterisk, possibly Iran does something different, I don't know. And also I am not a lawyer, but it is generally illegal to do any sort of trade in human tissues. You are not allowed to sell human organs. Everyone across the world pretty much agrees that selling organs is a bad idea. The side effect of that is also that there is no way you can make an agreement to that, maybe a contract that Alex would sign that says, oh, will you give your kidney to David today if we promise to give Bob a kidney tomorrow? There's no contract that sort of would allow that sort of thing to happen. I think I said that backwards, actually. Well, yeah, so I said that backwards. There's no contract you can give to Alice where you can say, Alice, will you promise to give your kidney away tomorrow if Bob gets a kidney today? So Alice always has the chance of saying, no, I don't want to go ahead. And Alice here is a person who is offering to give up one of their organs. So no one wants to even put someone in that sort of position where they're sort of forced to donate against their will. But that gives us into this weird quandary where, okay, well, we want Alice to donate to Dave if and only Charlie donates to Bob, but we can't sign any contracts or anything around this. So how do we get around this? And the best way that we have at the moment is doing everything at the exact same time, simultaneously. So this, the long-winded way, what I'm getting at here is saying that all 4 of these surgeries happen at the same time. So we got the transplant removing a kidney from Alice, and then at the same time, there's a nephrectomy removing a kidney from Charlie at the same time. And at the same time here means the 2 operating theaters are on the phone to each other, talking to each other. They are saying, yes, my patient has said yes, okay. The other patient said yes, okay. Both of the anesthesiasts put their patients under general anesthetic unconscious. Okay, are they both unconscious? Yes, okay. Now we both start the surgery at the same time. And obviously, since you want to limit the time that the kidney is taking between different bodies, the Bob and Dave surgeries happen at the same time as well. So what I am getting at here is that these two transplants means that we need logistically to have 4 operating theaters running. We need to have at least 4 surgeons, probably more, at least 4 anesthesiologists, and 4 sort of whole surgical teams going at the same time. And that is actually a lot to ask of any individual hospital. Even you might even need 3 or 4 hospitals to organize this together. And this is just for a 2 cycle. So if we allow sort of bigger exchange, so in this case, if we have 3 pairs and we have this cycle where maybe Alice donates to Dave, Charlie might donate to Edward, Francesca donates to Bob. This would be 3 transplants. That would be 6 surgeries happening at the same time. So this is something which logistically causes a problem. And it logistically doesn't mean we have to work out how to plan it. It means we might literally not have enough operating theaters to do it. It might be literally impossible. So in the end, what I'm saying here is that we are looking for some sort of set of cycles in my directed graph, but we want to limit the lengths of these cycles. The limit in particular, so for the UK, it's 3. For many countries in Europe, it is 3. For some countries, it is 2. And some countries are simply a bit more vague about whether they actually have limits or not. So I won't go into it. But generally, sort of about 3, it seems to be sort of the average where people say, yes, allowing cycles of size 3 is okay. More than 3, we don't want. There is, of course, one other problem with having cycles of size 3 or even longer. And that is what happens if someone gets sick. So in this case, I just put a red cross. Maybe the recipient was sick. Maybe the donor was sick. Maybe the donor changed their mind. Maybe some new medical incompatibility was discovered. So there's many things that could potentially go wrong. I mean, in this case, if that happened, okay, well, one person can't donate. Well, that's going to break this whole cycle. So even though only maybe one person got sick, that means 3 transplants cannot go ahead, which is less than ideal. You sort of want to avoid this as best possible. So one of the things we look for is these sort of embedded cycles, if you will. So in this case, we sort of, if the 3 cycle doesn't go ahead, we have a 2 cycle that we can use. And this is sort of fairly straightforward to do in this sort of case. You can obviously tell that this 2 cycle only works because it happens to be the correct 2 cycle for the arc that failed, or for the node that failed. If one of the other nodes had failed, the 2 cycle would also be useless. So there's lots of sort of subtleties that you can have going on here. And I'll talk a little bit more about what can be done in that setting. And even though I've described all of this, there's still one more feature that we sort of need to talk about. And that is something which is in pink here. So this is what we call non-directed donors for technical reasons, sometimes also called altruistic donors. This is a person who probably understands what a kidney exchange program is. Maybe they know a friend who has been in one or something like that. And they will simply approach the kidney exchange program and they will say, I want to donate a kidney. Not, I want to donate a kidney so my friend can get one, just I want to donate a kidney. I am just donating a kidney to other people completely altruistically. So this, of course, makes things a little bit more interesting from the optimization point of view, because these vertices, so in this case, I've got 1 and it's in pink. These will never have any arcs going into them, but they will just simply have arcs going out of them. And they're a little bit easier to optimize with because you're no longer looking for cycles. You are just looking for directed paths, which we call chains for reasons. So we've also had these sorts of structures we go. It's a little bit tricky here because I've said that cycles normally have a limited length. Chains sometimes do, sometimes don't. In America in particular, they tend not to worry about the lengths of the chain. And this is because once you start thinking about it, you realize, okay, well, the pink donor is not depending on someone else to donate a kidney. They're just willing to donate the kidney. So we can just do that transplant first. And then once that is done, then we have another person, a recipient who has gotten their kidney and their donor waiting to donate. And hopefully their donor is still going to donate. But if their donor says, no, I no longer want to donate, or if something unexpected happens, it's not going to be that someone has sort of lost out in the exchange. So people are a bit more willing to be relaxed with the simultaneous operations when it comes to chains. I say again, in some countries, I think the UK in particular does not take this approach yet, although maybe that's changing, I'm not sure. Okay, so a lot of that is coming
William,
out
a question?
Yep.
So in the example you had before with the 3 cycle that turned it to a 2 cycle,
Yep.
I guess for the topmost and the leftmost pair, they would be perfectly happy with the 2 cycle, but the reason we prefer the 3 cycle is that we're saving more lives.
Exactly.
So I guess there's a trade of like the willingness to go to longer cycles might depend on how many lives I save. So is there any sense you have on real world data, like what would happen if I would go to length 4 cycles, like how many patients would live, or not, doesn't really matter?
Yeah, so it definitely does matter. And actually one of the things that I do as part of my work actually is not publishing research articles, but actually testing these sorts of things, in this case for the UK, for the NHS and their system they run. I actually test to say, okay, if I take your data and if I allow, so for the UK, if I allow 4 cycles as well, this is what the change would be. It does increase, for the UK data in particular, it does increase the number of transplants, but we identify between 60 to 100 transplants every 3 months. We would increase that by maybe 2 or 3 if we went to 4 cycles. Now, 2 or 3, okay, people might look at that and go, oh, it's not a lot, it's a few percent. Every extra transplant is potentially a life saved when it comes to kidney exchange. So this is something where we really want the optimal, but also every extra value you can get out of the kidney exchange program is definitely worth something. Everyone really wants that. So even though it might only save 1 or 2 more, we definitely want that. The reason we haven't gone to that yet, though, is that it's a lot harder to model the likelihood of recipients becoming sick or medical incompatibilities coming up. So yes, bigger cycles are good, saving more lives. They will end up saving, they're not guaranteed to save more lives, obviously, but they're, in all our simulations, they do save a few more lives, 1 or 2. This is in the UK every 3 months. It's going to depend on which country you're looking at, obviously, but it's not easy to model the other effects of going to longer cycles. For instance, what is the likelihood that patients get ill? Because each patient, each donor, each recipient is so uniquely different that there's no standardized way of saying, oh, there's a 30% chance someone's going to get sick, because it varies so widely. So it's very hard to make any sort of guaranteed, yes, this is going to increase the rate of kidney exchange. It's just a case of, well, we'll identify more transplants and hopefully people getting sick won't affect it too much. I hope that answers the question.
Yeah, sure. But hidden here is also, like, at the end of the day, what optimization function we have, because I guess what you're saying is that for longer cycles, why would we worry that someone became ill, right? We just say, okay, we do it some other day. But then there's a cost, I guess, because all these surgeons were booked up and the operation theaters and everything. And that's like a hidden cost that we're somehow trading off against this extra life save.
Yeah, exactly. And so you sort of mentioned all the operating.
But does that go into is there an optimization function that has this as a term, or is it more like, no, we decide on 3 cycles and then we optimize?
There is definitely a list of optimization criteria. It is not it doesn't involve people getting sick. It is, let's skip a few slides. This is the optimization criteria for the UK. And I know I sort of jumped a few slides, so I'll talk about this in a bit more detail. Actually, what I'll say is, at least I want to mention that there is a kidney exchange program in Sweden. It was originally in Sweden. Actually, now it involves Norway, Denmark, Finland, and Estonia as well. They've recently started. Obviously smaller because there's fewer people involved.
So William, firstly, I don't want to interrupt you. Please take time to go through these slides, but there is an interruption from the chat also. So Massimo asks how likely it is that a 4 cycle is doable with 2 cycles.
How likely?
Like if you found a 4 cycle, and can you maybe, like, the likelihood of substituting it with other 2 cycles, or so is how I read the question.
Yeah. I don't know how to get the chat up once I'm presenting, which is annoying. Okay, so generally what we deal with when we get information, if I just go back to this picture here, so this is roughly what we get as optimization people when we're trying to solve this. We will get a directed graph. And if you look at this, I don't think this has any 4 cycles, but what we get is exactly the directed graph, and it may have 4 cycles, which have embedded 2 cycles, it may not, but we don't have to model sort of what is the probability of embedded 2 cycles existing or not existing. We simply get to look at the graph and say, okay, this is definitely our graph. Does this 4 cycle have embedded 2 cycles, and look at it from that manner. So sort of one step aside from that. We're not too far off anyway from where I was going. So just mention, okay, there is one in Sweden, there is one in the UK. I'm going to talk a bit more about the UK one. That's mostly because this is what I work with on a day-to-day basis, so I know it a bit better. And then again, the objective function. Every country has its own objective function / criteria. I think every program that I know of at least has a hierarchical set of objective criteria, not just one single one. So this in particular is the UK one. Let's see if I can, just grabbing a tablet to draw some pictures. Okay, so maximize number of effective two-way exchanges. This is sort of saying, okay, step one, look for two cycles that look like this and just find as many two cycles as we can that look like that. Again, so this is the way the UK program works, and this step one is just find as many of these things as possible. Step two, maximize the total number of transplants. That's saying, okay, well, we have a whole heap of things that look like this. If we have sort of, can we maybe extend that to look like this? So step two is trying to get as many transplants as possible. In effect, what it's doing is, okay, we have these. Can we find ways to extend them? Obviously, also, if there's like a completely separate 3 cycle somewhere that has no embedded arcs, we also select that. So first, we sort of try to find as many of these embedded 2 cycles as possible, then maximize the number of transplants. This will be selecting 3 cycles elsewhere and whatnot. There is this here, minimize the number of 3-way exchanges. This is trying to sort of say, okay, well, instead of having lots of 3 cycles, can we have just 2 cycles, but still get the same in terms of number of transplants and everything else? I will say at this point, these criteria were decided by this kidney advisory group, who they are not a set of optimization experts. This is a set of policy experts, kidney experts, surgeons, and that sort of thing. So they were trying to come up with something which they thought was ethically and legally made sense. It wasn't trying to sort of do anything mathematical in terms of what they were trying to optimize. The reason I say that is because actually this minimized the number of 3-way exchanges, this one here. It's not necessarily doing much use, and it might actually be doing something negative based on some recent results. Maximizing the number of embedded 2-way exchanges. So if we have, let me see if I can draw this correctly. If we have some weird structure that looks like this, so we've got a 3 cycle on either side of the central vertex. One has one of these embedded 2 cycles, one has 2. Then we choose the one that has 2 embedded 2-way exchanges. And then the last thing we do is, okay, now that we've done all of this maximization, we try to maximize some score, and the score is assigned to each transplant. And the score is basically like how long has the pair, so the recipient, been in the program, with priority given for people who have been there longer. Basically, the longer the wait, the more likely you are to get a transplant. The sensitization level. So this is a way of giving recipients a number, where a number of 0 means very likely to find a transplant. A value of 100 is very low likelihood of finding a transplant. So again, trying to prioritize those people who we have trouble matching. Then there's also things like the level of tissue type matter. So a measure of how medically good is this transplant, and there's also a bit on age difference between donors. The whole point of this score is not necessarily to try to, okay, it is trying to do the most good. One of the extra things this score is trying to do is trying to guarantee that there is just one optimal solution, because we don't want to get into a case where there's possibly 2 optimal solutions and the algorithm gets to choose between the 2, because ethically that might get hairy. Let's get rid of that. Okay, so that's the objective.
Would the actual number of transplants, would that change between steps 4 and 5?
No, so this is all completely hierarchical. So at step 1, we work out how many of these first 2-way exchanges we can get. In step 2, maximize total number of transplants. We sort of fix that as in the integer programming model, we fix that as constraint. The number of transplant must equal 170 or whatever we get. And then subject to that, we try to do all of these other criteria.
Got it.
So these are all hierarchical. Okay, so so even if we just look at maximizing the number of transplants, so I've told you how the UK system works, which is going to be relevant in a bit, but even if we're just maximizing the number of transplants, we can do that in polynomial time. If we have 2 cycles only, that's a matching in a graph, if you want to look at it that way. It's also polynomial time if you allow any length cycle, but otherwise it's NP hard. And I say almost exclusively solved with integer programming. I believe there has been an attempt to use constraint programming, but as far as I'm aware, all of the actual kidney exchange programs, so the actual programs running, they all use integer programming techniques. actually, that's a lie. I know of at least one that doesn't. They either use integer programming techniques, or their program is so small that they can do it by hand. So there's programs, I think in the Czech Republic, they have maybe 6 or 7 pairs. So 6 or 7 vertices in their graph, at which point you can sort of look at it by hand and go, okay, this is the best, we'll use that one. But in general, it is going to be integer programming techniques. This is one thing that I've been working with Jacob a bit on, trying not just using integer programming solvers to try to solve these problems and seeing if there are different techniques which might have better or worse approaches, for reasons which will come up in a second, because let's talk about the models that we use.
Just another question out of curiosity. Yeah. I mean, in these, well, this is maybe the wrong question to ask to someone in the United Kingdom, but the rest of Europe is still somewhat united, maybe, perhaps. And so, like, what would happen if we pooled all the kidneys together?
That would be really good, just to begin with. Yeah, so lots of countries do different things is one of the problems. And by different things, I mean, this is also legal issues. So I believe it is in France, it is illegal for the donor and kidney, or the donor and recipient to meet each other through the kidney exchange program, if that makes sense. So if I go into kidney exchange program and I'm going in there with my friend who I already know, and it ends up being that my kidney somehow goes to that person, that's okay. But if I'm going into a kidney exchange program and my kidney is going to some other person, then legally I'm not allowed to find out who that other person is. So this is the way it is in France, I believe. But then in other countries, it's almost the complete opposite, where it is a legal requirement that they meet and at least talk to each other and say, yes, I agree to this before the transplant happens. So there's legal reasons why we can't even do it necessarily. And people are trying, obviously, to sort of lobby and so forth to change the rules, but there's those sorts of things. In general, it would be very good. One thing that I've skipped over a little bit, I talked about tissue type compatibility. This is something called presence of HLA, so human leukocyte antigens. And the presence of these is something that is roughly following genetics, which means that, and I said, it roughly follows genetics, and also once you have a transplant, you're likely to sort of build up antibodies from similar genes again. So the best thing to do is actually to have people from different genetic backgrounds when you are trying to find these possible transplants between donors and recipients. So if you can actually find a kidney, or create a kidney exchange program that does include people from diverse genetic backgrounds, that is actually a huge bonus, huge benefit to these sorts of things. But as I said, it is tricky because there are sort of legal and ethical issues. Just quickly with regards to what's happening in Europe, Portugal, Spain, and Italy do a little bit of collaboration. The Czech Republic and Hungary do a little bit of collaboration. France does generally its own thing. The Netherlands does generally its own thing. I've mentioned that Scandinavia plus Finland and Estonia have started STEP. So, but that started, I mean, I think it started at the end of 2019, but obviously pandemic has made that a bit awkward to get going. And I think, I can't remember who, but Israel collaborates with someone in Europe as well. So people have started doing these sorts of collaborations. It opens up a whole new set of problems for us optimization people to solve. Hope that answers that question. There's a bit more rambling, I think, than I intended.
Yes, thanks.
Yeah. So just quickly, so we have these, so we're talking about integer programming. So two of the first models introduced, this was in the late 2000s by Abrams, I think. So there's edge formulation and cycle formulation, and most people who do optimization and kidney exchange knows what these mean. Edge formulation is just assign a variable to each edge. So it's a binary variable, 1 if you select this edge, 0 if you don't. You set flow constraints on each vertex to make sure that you've got at most 1 incoming edge and most 1 outgoing edge. And then you've got to add a whole heap of constraints to say that you can't have long cycles. So there's an exponential number of constraints, but a polynomial number of variables here. And then there's a cycle formulation, which is enumerate all of the possible cycles. So possible here meaning up to length 3 or 4 or 2, whichever one you want. Have a variable per cycle, and then constraints to make sure that you don't select more than 1 cycle for a given vertex. So exponential number of variables, but at least you've only got a polynomial number of constraints. So there's sort of the two basic ones we work with. And this here is why I sort of thought that pseudo Boolean solvers might be something useful, because we don't have I think in general, we never have any real valued or integer valued variables. All of our variables are binary. There are also obviously other models. So there's the extended edge formulation, which tries to reduce the number of constraints you have in the edge formulation by introducing more variables. So TSP formulation, so this is just trying to use traveling salesman type approaches. So I think it was PCTSP they used in particular there. And then there's also this position index chain edge formulation, which sounds a bit confusing. It's a decent model that has been derived. In particular, it's, I think, the first compact model. So it has both polynomial number of variables and polynomial number of constraints. There are a few caveats. In particular, it cannot model the last objective in the UK scheme. So it is a little bit tricky to model all of the different objectives that we have sometimes. So those are different models that we've done. Okay, so the TSP is a TSP formulation, but otherwise these are all generally integer programming formulations. There's also the usual sort of branch and cut approaches, branch and price and cut. There's also this improved hierarchical optimization, which I'm going to talk about probably maybe in the next hour after the break. But people have been trying sort of other things as well as new models. One thing I do want to point out here is that there hasn't been much work trying to look at other techniques outside of integer programming. So I mentioned I've started looking a little bit with trying to use pseudo-Boolean solvers to see if I can get anything different. Nothing concrete has sort of stood out yet there, but I'm still hopeful. I think maybe someone has tried constraint programming, I want to say, but I mean, Kieran might even know more than that, but I don't know if anyone has actually gotten any sort of interesting results out there. So it very much feels like people have spent a lot of time looking at the models. People have spent a lot of time sort of looking at integer programming techniques, but not much has been done in terms of trying to use any other techniques to improve this solving time. And I should say, yeah, so the big thing people are interested here is solving time. So we want to solve to optimality, obviously. The UK program at the moment takes a couple of minutes to find an optimal solution just for the UK. One of the reasons we don't have a Europe-wide collaboration, one of many reasons, is that we simply could not solve those instances in any reasonable amount of time. We would expect to have maybe 1,000 or so donors and recipients, and it would just be an enormous amount of computation power to try to find the optimal solution in all of that with current tools. I say that some of these papers do actually manage to solve sort of 1,000 plus. There is a star on almost all of these papers in that almost everyone does simulations rather than working with real data, because no one can access real data really. And when I say that, I mean, I can test on real data. I cannot give someone else real data to verify my results. So I have to generate fake random instances and then send those fake random instances out so people can verify my results. So a lot of work that is done on these random instances, and there is a huge asterisk as to whether those are actually accurate or not. Paper forthcoming on that in a few months, hopefully. Just quickly before we maybe cut to break, I just also want to say robust optimization is actually one other thing that's being looked at a lot. So this is where we know that donors and recipients can fall, or transplants might be unviable. I've talked about these back arcs, these embedded sort of cycles that we can have. We can actually, and people have actually assigned probabilities of failure. So this is where you say, okay, well, this edge has an expected failure rate of 0.2 or something like that, and that would adjust the value of that transplant just directly, basically. Again, the problem is that this has been modeled with constant probabilities of failure for each edge. So every edge has the same chance of failing, which is definitely not true in the real world. And there is, people have yet to work out what these probabilities are, or a good way of modeling what these probabilities are. Because obviously you don't necessarily know if someone is going to get sick until the point they do get sick, at which point it's too late to do any optimization. The other thing that people try to do, so these back arcs, these embedded cycles, are sort of a very limited way of saying, okay, if this person fails, what can we change to find another solution that's just as good? People have looked at sort of that in a more, in a looser sense, in the sense that you're allowed to do more things to the solution. So if you maybe get rid of a vertex, maybe you're allowed to change things within distance 2 of that vertex, so change the solution and sort of see, okay, well, if I change the solution within distance 2, how good or how bad is the new solution? What promises can I guarantee? How long does it take to find those changes?
William?
Yes.
Since you're talking quite a bit about failures, should we deduce that these are actually somewhat not, and I mean, there is somewhat non-infrequent events?
Yes. Sorry. They're definitely not infrequent events. They're definitely frequent events. One of the, sorry, I'm going to jump through the slides for a sec here. This one here. So this one here, I think, really starts to point out. So this has been run, this is the UK system, just some statistic. It's been running since 2007. Matching runs happen every 3 months. We have sort of order of 200 to 300 pairs per run. So if you think about that, that's sort of 800 pairs per year. You'd expect 8,000 pairs over the, well over 8,000 pairs, 10,000 pairs since 2007. And we've only had about 1,000 transplants. So one of the things that does happen actually is that a lot of the transplants that we hope will proceed end up not proceeding. And I think it's somewhere in the order of 10 to 20%. And these 10 to 20%, again, because it's medical data, I can't tell you why, because I don't know why they fail. So sometimes it is, oh, we thought this transplant was possible. Turns out that there's some medical incompatibility we didn't anticipate. Sometimes it might be, oh, the donor died unexpectedly. The donor is sick. The recipient is sick. The donor might have just changed their mind. The recipient might have gotten a kidney from a kidney exchange, deceased donor waiting list. So there's many reasons why these can fail. We don't know why they fail because it's personal medical data. So it's something that hasn't been shared with us. But I can say that sort of 10 to 20% of identified transplants generally won't go ahead. And this is in the UK where things are pretty good. In, for instance, the US, it's a much different system there because kidney exchange programs compete against each other inside the healthcare system, but they have somewhere around 50, 60% of identified transplants don't happen. So more than half of transplants won't go ahead. So failures do happen a lot. Unfortunately, we just don't know how to sort of accurately model that because it does not seem like it's a homogeneous failure rate. It just seems to be specifically maybe certain people are more likely to become ill or something like that.
Okay, thanks.
Yeah. And I think, given where I'm going next, I think we might leave it there for now. Let's jump through some slides. If you're going to stick around for the second hour, you might see some of those slides, but we'll leave it there for now. And I think we're going to be taking a break, but I can always do questions before the break. And then afterwards, I'm happy to go into more detail on either anything that you've seen here or actually, sorry, skipping slides again. Quick read the numbers. Otherwise, I've also got some more slides. So these are slides looking at this improved hierarchical optimization. So this is looking at integer programming and linear programming techniques that we've taken advantage of within kidney exchange program. So it's very much linear programming, integer programming techniques, a lot less on kidney exchange, if you were interested in that for the second half.
Okay, so are there any questions or comments? Otherwise, the plan is to have a break that I think is, say, long enough to go grab a coffee. So yeah, like 5-10 minutes. But I don't, I mean, and we'll pause the recording during the break, but it's, people are of course allowed to talk also during the break. I don't see any question right now, so I hereby officially declare a 10-minute break.
All right.
So we're back after the break and we're starting with a few questions and then we'll let William continue.
Okay, so I have one question regarding your encoding. You have a case where you might have an explosion because of the number of constraints, because of the cycles. So did you try to have to reduce the number of constraints and to try to gather a solution from the solver and then to check it afterwards? This is what we usually call CGAR. It means you start with a a small number of constraints, if you are lucky, well, good, you get the solution, or else you add more constraint to refine the model and to have to constraints more the solver to provide you a better solution.
Okay, yep. So I will say, so firstly, I haven't done anything like that myself. I do know people, so the closest I can think of that's been done along those sorts of lines is people who are looking at branch and price and cut, those sorts of techniques. That's the closest I can think of to this sort of thing. And that was all, as far as I can recall, explicitly done for integer programming sort of solvers. So it was very much tested and applied to integer programming and not to constraint programming or any pseudo-Boolean or anything else. I think it's definitely something that's worth having a look at. I think the general feeling, so this idea of having an explosion in number of constraints, that comes from having this edge formulation where you have a variable for each edge. And for good or for bad, people seem to be very settled on not using that formulation. And it is because of this explosion in the number of constraints. So again, so a few people have tried doing this sort of branch and cut sort of approach. It's not the favorite in the crowd at the moment. That doesn't mean it wouldn't be good to sort of study that a bit further, and maybe because it hasn't been studied, it's worth studying a bit more.
Okay. But and regarding the benchmarks, because then you have randomly generated benchmarks, so we can find them somewhere on.
So I will type into chat. So it's just called preflib.org. I'll type into chat just in case people didn't understand that. It does have kidney exchange instances on it. I will also add the caveat, and I'm sorry for doing this now. Those instances were generated in, I think, 2000, somewhere in the late 2000s, so before 2010 or around 2010, I think. In particular, some of the instances definitely had bugs. So I've spoken with the authors and they've agreed, they actually found where the bug was in their code that generated the instances, and it meant that some of the edges were wrong. On top of that, there is a paper which I am at the moment sending around to co-authors to just double check everything, so hopefully submitting soon, which basically points out that those instances, even if they were generated correctly, are not a good match for the actual instances that we have in the real world application. The big problem is that, so the edge density, so the number of edges that are there versus could be there, is about 20% in the random graphs. In the actual models that we have, so the actual data, it's closer to about 10%. And that obviously has a huge effect on which, not just, okay, the solutions are different, but having a much lower edge density means that it's much harder to get good, tight upper bounds. So it completely changes which algorithms work well and don't work well. And I'm sorry, I'm saying this sort of just as the paper is not yet out there, so I can't give you anything, but hopefully in the next few months, I'll be able to have something out on that.
Okay, good.
So is there any, so it's hard to collaborate across Europe on the donor recipient side, but in terms of algorithmic development, are people in different countries running different algorithms, or is there like a network of researchers so that you all run the same algorithm in different countries, or?
So there's a little bit of collaboration. So the UK runs our own code and algorithm that we wrote ourselves. I think pretty much every country that runs software uses either, I think most, if not all, use CoinOR, so the free open source MIP solvers. And this is because most of the pools for individual countries are small enough that runtime is not an issue. The runtime issue is going to happen if we start collaborating, and sort of one of the reasons we can't collaborate very well. Having said that, I think the Dutch have software which I believe is in use by Spain and maybe Portugal. So there's sort of ad hoc agreements here and there where some people might share code and algorithms. I think most places, I think actually STEP, the Scandinavian system, I think they are starting to use the same code that was developed in combination between Portugal and Hungary recently. So there is a little bit of collaboration in sort of having the same code and algorithms. It's not quite on a Europe-wide scale. It is very much sort of ad hoc agreements here and there. And again, I'm just like, in terms of algorithms, it is generally just IP formulations, and people are generally going to use the cycle formulation, so a variable for each cycle. And the objectives are going to be just different between the countries because each country has different priorities. There is a publication out which actually looks at all the different objective functions and hierarchies of objective functions that the countries have. They all sort of have similar things in that, okay, get as many transplants as possible, try to have some sense of robustness or fallback options, and try to promote transplants to those people who might find it harder to get transplants. So the same general ideas, but every country has its own unique sort of twist or tweak on how to do it exactly. So everyone has their own objective functions, basically.
Okay, makes sense.
Yeah.
And this fact that you say that edges sometimes disappear, and like you find your beautiful cycle and then it isn't a cycle after all, is that like because once you identify candidates, then you will do like in-depth medical tests and see that, oh, this wasn't as great as we first thought?
Exactly, yeah. Yeah, so these tests, they're called cross-match tests, and a positive cross-match test is a bad thing. So it literally means taking some sort of, I believe it's blood, I could be wrong, some sort of medical things from both people and putting them together and seeing how they react, essentially. So that is how we actually test to see if the transplant is likely to be compatible, at least. That is an expensive test in terms of money, in terms of like resources. People have to sort of do this physically in a lab and then look at what's happening. There's no way to really automate that process. So we don't do those tests until we have identified sort of our optimal set. So taking a step back, the way it works is they will look at the HLA profile. So I'll talk about this HLA thing. It's some way of describing what antigens a person has. They might have some idea of what antibodies someone else has. They look at that and go, oh, we think this might be good, or we think this might not be good. And it's very much a sort of rough estimate of, do we think this is going to work, yes or no? And that's the information we get. It's an indicator. So from the optimization side, we definitely just say, yes or no, this edge is here, we'll optimize based on that. But really what the data is actually saying is, we think this is plausible. So each edge is not actually guaranteed to exist. It's that we think this is plausible, find us an optimal set. And once we found this optimal set, that's when they'll actually go in and do these actual lab-based tests. And that's when, yeah, these edges might disappear, along with things like, of course, if people get sick or something like that.
The last time I spoke to John Dickerson, he was claiming he had a machine learning system that could predict which edges were going to disappear. And that struck me as very, very scary.
I've heard similar things. I've spoken to him about similar sorts of things as well. It's a bit worrying, in part. So I've tried not to talk too much about the US system. So John is working in the US system, I think with UNOS, which is one of their kidney exchange programs. And because America is America, they have many kidney exchange programs which compete with each other. This brings up many problems. In part, they want to be the first to identify a potential cycle, because if they identify a cycle before some other organization, then they get those transplants, and therefore they get the money, they get the prestige, and they get the reward and all of that sort of thing. But that also means that one of the big reasons edges fail in America is literally, oh, a different kidney exchange program organized that transplant, not us. So I don't know. I know what his results are, and they look promising. But at the same time, I feel like his results are only applicable to the US because they've got this competing kidney exchange programs things, which Europe just does not have. So interesting, but at least it's not going to affect the EU, I hope. And yeah, it is also slightly scary because I don't know exactly, and I guess no one really knows exactly what this machine learning algorithm is doing to decide, yes, this edge is likely to fail, or no, it's not, whether it's health medical issues or whether it's looking at something else.
So another thing is, so I think we should let you start speaking very soon, but I just, one question that, because this hierarchy of optimization criteria and the importance of splitting ties so that it wasn't some kind of arbitrarily algorithm implementation, that there was like some kind of more fundamental reason why this is the right solution, it sort of brings up the question, strictly theoretically speaking, it could be that your code isn't doing exactly what you think it is because there might be a bug in it.
Yep.
Is this something that has at all been a concern, that maybe we're not computing according to this criteria?
It definitely has been a concern to various people. Depending on who you speak to, you'll get different answers as to how much they care about it, how much they've looked into it. For instance, here in the UK, at the moment, we just use a cycle formulation, so it's fairly straightforward. There's not much in the way of fancy algorithmics involved from our side. It is just enumerate the cycles and then throw them into a solver. We use the CoinOR solver. We assume it is correct. We just assume it is. That's just the way it is at the moment. I guess people who use Garobi or something like that probably do a similar sort of thing. That code, though, which is, I've tried to explain, it seems like it's fairly straightforward code. That code took about, I think, 1.5 years, 2 years to write, because there is a lot of testing of any of the code that we wrote. So this, we here being school of, or an employee of the School of Computing Science here in Glasgow. So the code that we wrote, the enumerating of the cycles and that sort of thing, it did actually go through fairly reasonable / comprehensive testing. So the NHS was concerned about that, but they seem to be happy to accept that the CoinOR solvers may be faulty, and they assumed that they weren't. That's the situation in the UK. I know other countries, let's say, I don't think all other countries are quite so even that comprehensive when it comes to testing. I'm sort of hedging my bets here because I know this is being recorded, but yes, I have concerns about the way some software that some countries use has been written. Yeah.
Fair enough. So, and how will you entertain us now?
I mean, if we have no more questions, what I was going to talk about, so actually going to talk back about this hierarchical optimization thing. I'm just going to sort of talk through, it's probably not going to take the rest of the half hour that I have left or anything anyway. Let me share my, I mean, yeah, there's no more questions, so let me share my screen again. That one. All right, so we were just talking about this hierarchical optimization, and just sort of give you the mathematical definition if you haven't seen it. We've got a sequence of objective functions. So it's a sequence in order. So all we do is we maximize, let's pretend they're all maximization for now. We maximize the value of the first objective function called O1, and then just add that as a constraint. So it's maximizing the second objective function subject to the first function already being maximized. So we're not trying to find any Pareto front or anything like that. We're just trying to find one solution, hierarchical optimization. So this is how almost all kidney exchange programs work in the EU at the very least. What we've done is we've sort of tried to realize that, okay, we don't really care about the solution at each point. And solution here, I mean specifically, I don't care about which cycles are selected at the first point. All I care about is what value did my objective get at the first point. I only care about the solution once I've found sort of all 5 objectives, once I'm solving for the last objective. So what we're doing is a technique called, or what we're calling diving. So here is just an example where I'm just sort of step through it very briefly first. There's about 4 examples, so we're going to slowly build up a bit more complexity and see why this works, why this doesn't work. So here I've got, say, an example. So I'm not going to give you the program or anything. I'm just going to say there's 5 objectives. LR, linear relaxation. So all we're doing is we're just going to solve the linear relaxation and assume that we can reach as close as possible to that value. So on the right-hand side, I've got here the IP value. So this is the actual value of the integer program if we try to solve for this objective. We don't actually know. This is just this sort of, for us, we can now see what the actual integer programming value would give us, but we're just going to assume that linear relaxation is going to give us as tight a bound as it can. So if we were trying to do this, we sort of, okay, for the first objective, we just solve the linear relaxation. We get a value of 127.3. Obviously, if this is an integer program and assuming we've got integer coefficients in the objective function, some people don't assume that for some reason. Then we can assume, okay, well, 127. We can't do more than 127 for our first objective because we've got a linear relaxation. So let's assume that we can get 127 and then just go to the second objective. So again, we solve the linear relaxation of the second objective, get 96.2. Okay, well, let's assume we can get 96 for our second objective. Do the same for objective 3, we get 42. And then we do the same for the objective 4, we get a linear relaxation of 1,047.03. So we assume, okay, well, we assume we can get 1,047. At this point, you can sort of see that the assumption is not the same as the IP value. So what this means is that, like, us running the program, we don't know that yet, but actually we're looking for an infeasible solution here. And then we get to the 5th objective. The 5th objective we just solved normally. So at the 5th objective, this is the first time we solve an integer program. So before this, we've just solved 4 linear relaxations, 4 linear programs, polynomial time, whatever method you want. So for our first integer program is infeasible. And you can sort of see where I'm going with this here is I'm trying to skip as many of the integer programming steps as possible so we can just do linear relaxations and then just solve as few integer programs as possible. Okay, so our first integer program was infeasible, which tells us not much. It tells us that one of our assumptions must be wrong, but it doesn't tell us which one. So in this case, we sort of try to do something smart. And again, this is sort of the first example. So something smart would be to look at the linear relaxations when you realize, okay, well, 1047.03 is only a tiny bit more than 1047. So maybe it was actually that the 1047 was wrong. So we'll try changing that. So, okay, instead of assuming it was 1047, we'll try 1046. And then we solve for our 5th objective. At this point, we get an optimal solution, and we can say, yes, we're done. This is going to be, therefore, be the optimal solution. We know we can't do any better than 127 for our first objective because we've got linear relaxation, same for objectives 2 and 3. And for objective 4, we know we can't do more than 1047. We can't do actually 1047 because that was infeasible. So 1046 must be the best we can do. So therefore, we have our optimal solution. So this is a very, very ideal way that this diving would work. Obviously not going to work like this all the time or even most of the time. So let's look very quickly at a slightly different example. You can see that the value of, so 2 things have changed here. So the IP value of objective 2 is now 95, not 96. So we've got another place where our assumption is going to be wrong. And also the actual linear relaxations have slightly changed to sort of make the example shorter. So again, we sort of work out our linear relaxations. The first IP we try to solve has these assumptions. Turns out it's infeasible. So then we go through again, we go, okay, well, 96.2, that's actually the sort of closest to our assumption that we have. So because it's only 0.2 away, whereas in objective 4, we're 0.24 away now. So we do the same thing as before. We change our assumption. Instead of assuming 96, we assume 95. Obviously, this is going to change our linear relaxations now. So all of them have gotten smaller. Obviously, they can't get any bigger, but they might stay the same. But in this case, they've all gotten smaller. But we still get 1047 for our assumption for objective 4, and we can still see that is too big. So we would still get an infeasible. So this tells us, okay, we still have one of our assumptions is wrong. So now we just go through and we just repeat the same process. We go, okay, well, looking now at our linear relaxations, we're back to this 1047.03 value. Very close. We can try knocking that down 1. So now we try 1046. So at this point, 2 things. A, we have shown that we have an optimal solution with our assumptions. We've already solved 3 integer programs, and just solving the original problem would have been 5. So we're not actually that far ahead anyway. But just because we have an optimal IP at this point does not even mean we have an optimal solution to our original problem. So one thing to be aware of here is that we know that, for instance, this problem here was infeasible, where our assumption was where 127, 96, 42, and 1047. We know it was impossible to get 127, 95, 42, and 1047. And we know this was possible. But what we don't know yet is, what if I tried 127, 96, 42, 1046? So what if it was just our assumption of objective 4 that was wrong? Maybe our original assumption in objective 2 was right. The algorithm doesn't yet know that. So actually, we would also need to solve another integer program to show that we cannot actually get to 96 on our second objective. Now, this is not the only way to sort of finish off this proof that we have an optimal solution for this problem. But whatever we do, we would still need to solve some other integer program. So at this point, we're solving 4 integer programs, 3 of which are infeasible, instead of solving just 5 integer programs, all of which would be feasible. So it's easy to see that this sort of diving approach, where we sort of assume our linear relaxations are good, is like in ideal situations, it can work out great, but it can so easily and so often go horribly wrong. So it's sort of ideal where you sort of think about it, and for the first 5 seconds you think about it and you go, oh, that sounds like a good idea. And then 3 seconds later you realize, oh, wait, that's almost always going to be a horrible idea. What we can do though, is we can do a couple of things. So one thing I'm doing here is I've got these solved normalies in the middle now. What this means here is I'm just trying to make a checkpoint. And this is checkpointing in sort of your usual algorithms. And I'm trying to say, okay, rather than trying to do my assumptions for all 5 or all 4 objectives, I'll do assumptions for 2 objectives, do a normal solve, do some more assumptions, do a normal solve. And these checkpoints mean that I can sort of verify, are my assumptions up to this point correct or not? So at this point we're solving, so I've got solve normally written first on line 3 here. So in this example, I'll make 2 assumptions for objective 1 and 2, and I'll try to solve for objective 3. And we can see that the assumption on objective 2 is 96, but the actual value is 95, so it's going to be infeasible. So I need to take, well, at least one of my assumptions down. Again, I take the 96.2 down to 95 because 0.2 is less than 0.3, and then try to solve again. And what this does now, it's sort of doing similar things to what it's done before, but now I know that I can't do any better than 127 and 95 in my first 2 objectives. Because I know I can do 127, 95, 127, 96 didn't work. Anything bigger than either of those 2 is not possible due to my linear relaxations. So it sort of gives me a sort of an easy way to check the assumptions I've done so forth. And then we just do basically the same thing again. So we get an infeasible when we try 1047, we try 1046, that works. So checkpointing sounds like it might be useful, then you realize, well, I've still solved 4 integer programs. I'm still barely doing anything better. So there is something else we can do, and that is we can recognize when our objective functions are going to give us good / close to tight linear relaxations. So up until this example, I've sort of told you that it's always been objective 2 and 4 where things have gone bad. It's always been objectives 2 and 4 where we had to sort of take our assumptions back a step or 2. So what if we just say, okay, well, objectives 1 and 3 seem to have good linear relaxations. So we'll just make the assumptions on objectives 1 and 3. That actually works pretty well because we just solve optimality for objective 2. And that gives us a solution because our assumption is fine. We do our assumption for objective 3. We solve objective 4 normally, solve objective 5 normally. We get 3 optimal solutions, 3 optimal results from the solver, and that gives us our solution. So in this case, and again, I'm going to stress, if we actually know that our objectives 1 and 3 give good linear relaxations that are close to the integer program, the integer value, then we can just skip those ones. So this is not something that sort of applies to any arbitrary integer program, but in our particular case of this kidney exchange program, we might know that certain objectives we can often get good tight upper bounds through linear relaxation or other techniques indeed. So this is one of the things we do with diving. One thing that I think I've got time to talk about briefly here is there's actually another subtlety that we can do here. If I step back to, yeah, so let's look at this slide for a bit. So this is the slide we already see. What we see here is actually, sorry, let me go back to this one here. So this is the very first example we looked at. What I want to look at is objective 4 here. The linear relaxation says 1047.03, and our assumption is, okay, well, let's see if we can get an integer value of 1047 for this. If we want to get an integer value of 1047, we can look at the linear relaxation. What we can start to do is we can look at so if we look at the dual problem in the linear programming sense, the dual problem, we can look at essentially the cost of each of the variables. And we can look at any of the variables which are current, like any of the basic variables, look at the cost associated with that. And we can sort of look at, okay, roughly speaking, it'll give us a sense of how much will it cost us to change this variable from a 0 to a 1. And if we know that we sort of want to only lose at most 0.03 from our objective value or something like that, it gives us a bound on what costs are definitely not worth taking. And if we apply that to the basic variables, that means there's a whole number of variables that we can remove. So I'm sort of running through this a bit quick because I wasn't planning on getting through this much and this quickly. Feel free to say something if this is confusing, because it might be. Seems like people are. But yeah, so if we look at the linear relaxation, we look at what our assumption is, it gives us a sense of, okay, how much can we lose through changing some of these variables? And if we look at the cost of those variables, it makes it easy to take some variables and decide these variables must be set to 0 no matter what, if we are to reach the assumption. So it is still this very much tied into with making these assumptions. If we don't have the assumptions, then it doesn't make sense to do this anymore. So what I'm trying to get across with this, and I don't have the numbers for you off the top of my head, unfortunately, sorry. If we do this second part as well, so this is where we are deactivating variables, essentially. We're saying, okay, the cost of these variables is too high to ever possibly reach this assumption. We found that in our examples, we can deactivate approximately 90% of variables. So we can sort of turn a problem with 100 million variables down to maybe 10 million variables or something of that scale. And this can make it a lot faster to solve all of these in between integer programs that we're solving. So when we get to sort of this sort of case here where I've said, okay, well, we still have to solve 4 integer programs. If we take the right steps and we are deactivating these variables, each of these integer programs can actually be a lot quicker to solve as well. So not just are we solving fewer integer programs, but these integer programs that we are solving along the way can often be a lot quicker to solve. Hopefully that makes sense.
I mean, the general, I think it makes, of course, we don't know the details because we don't see the problem, but it sounds like a large number.
Yeah, no, this is definitely something that it was one of those things where we were impressed by how well it worked. Again, I really do want to stress that all of this stuff that I'm talking about, so diving and deactivating variables, this all completely depends on the problem you are solving. So it works for us well on certain objectives in kidney exchange. It's not the sort of thing which you can arbitrarily apply to any solver. It's going to be the sort of thing where you have to selectively choose to do it when you have a detailed understanding of the domain you're working in.
Mm-hmm. Okay.
But yeah, so this is one of the sort of 2 things that, well, I guess 2 of the 3 sort of things we were doing with this. The last thing I'm going to quickly mention, again, so this is all in the context of hierarchical optimization. Going on to this slide. So I have shown you, at least we talked in detail about, I guess, 2 of the models, and there was 4 or 5 other models listed. One of the things we have worked out through testing with all these sort of things is that actually, if you have multiple objective functions and also multiple models, it might well be that certain objective functions are quicker to solve using different models. So this is actually something that we have observed, and we're writing the paper at the moment. We have observed that in the kidney exchange program, I think it's the cycle formulation is actually faster for, I think, the first 2 or 3 objectives in the UK scheme. And then after that, it actually turns out to be better to use the edge formulation. So what we're actually doing here, like in our paper at least, we are actually solving the first 2 or 3 objectives using the cycle formulation. We take the result that we have there, translate everything over. So of course the variables are changing and the constraints are changing, but also we need to sort of look at what values the objective function reaches and appropriately translate that to count the right things. But what we've actually found is we can actually find a decent speed improvement simply by swapping between 2 models. This is very much a sort of example I've got here in front of us. So in this case, I was trying to be a bit more generic than talking about kidney exchange specifically here. If we got 2 different models, I called them IP1 and IP2. You can see that IP2 is a lot faster at solving the first 2 objectives, right? Almost order of magnitude for the first one at least. But then IP2 is a lot slower for the 3rd, 4th, and 5th objectives. So if you are able to sort of translate between 2 different models, if you can sort of work out exactly what needs to change, how the constraints might change, and how the objective values would change, it does take a little bit of computational time, obviously, so you do need to take that into account. But we actually found also another significant speed up improvement in doing this. And what I can say is sort of taking all of these sorts of results, so these 3 things that I've mentioned here in this sort of second half hour or so that I've talked, these took, so on kidney exchange problems, I said the UK has 200 to 300 pairs. If we take a problem on about 600 pairs, if we try to solve that for the UK system, it takes somewhere in the order of half an hour to an hour. If we implement our changes that I talked about in this last half hour, so this diving, the deactivating of variables whose costs are too high, and also switching models halfway through, we take that sort of half hour to hour time down to sub 1 second. So less than a second to solve these instances now, which A, is great because we have a good result. B, is slightly annoying because we no longer have a reason to do more study in the field because we can solve everything almost. But as I've sort of mentioned, this is incredibly good numbers on randomly generated data. And this is where I sort of discovered the problem, because that this randomly generated data does not quite accurately reflect what happens in the real world. So somehow we have very good results for artificial data, which does not translate to real world scenarios. And this again sort of ties back to this where I talked about edge density. Because the edge density is lower in the real world instances, that means the linear relaxations and other upper bounds are no longer as tight. And that means that this diving and deactivation thing doesn't work as well, which means that annoyingly our work is not quite as applicable as we'd hoped it would be.
When you're getting the change from a model switch, is that because it becomes easier to find the solution or easier to see that it's optimal, or both, or do you know?
I actually don't know that. Now that you say that, I want to go looking into it. Yeah, I don't know whether that's finding an optimal solution or proving it's optimal. Yeah, sorry, I really don't know. I want to go find out, but I don't know at the moment.
Okay.
And yeah, I think, I mean, the rest of the slides are basically things that we've talked about. I guess one other thing that I just briefly want to mention, because we talked a lot about collaboration between different countries in the EU. And I've also spoken a bit about the fact that we have different legal systems, but also different objective functions. One of the areas that's getting a decent amount of interest at the moment is also ways in which countries can collaborate. So the obvious sort of thing to do is just take all of the participants, put them into one giant pool, and everyone sort of collaborates together as best possible. That is an ideal situation, but another way to sort of work through this sort of system is to have maybe Scandinavia, maybe the STEP system does all of their kidney exchange work. The UK does all of their kidney exchange as much as possible. And then the people who have not yet been matched might go into a pool. So this is sort of somehow just taking those people who did not get matched nationally and just putting them into an international system. And those two ways are sort of relatively straightforward to model, but people are starting to look at in-between ways of doing this. So can we maybe do a model where we have everyone in the one pool, but different objective functions apply for different sections of the pool, or maybe different constraints. Maybe you're allowed to have cycles longer in the STEP program than in the UK, maybe. So people are looking a lot at that sort of thing. This is turning out to be unsurprisingly more complicated than we thought, but that is definitely one of the areas that people are interested in sort of trying to work out more collaborative results. There's a lot more actually economists are also interested in this, because there's a lot more talk about collaboration and like individual rationality and those sorts of concepts is involved in that as well. But yeah, I think that's the end of what I had planned to talk about. If everyone, unless people have questions.
Yeah, I have one question regarding the benchmarks. So we know pretty well in SAT that having random benchmarks or having crafted benchmarks might be quite different from, well, application benchmarks.
Yep.
And it was especially the case for MaxSat, where at the beginning we had a lot of, we didn't have real benchmarks, so we were evaluating the solvers on random benchmarks. And you have at the end of the day, when we started to have real benchmarks, it happened to that the approaches that work very well on those benchmarks were completely different from the ones that were initially designed on random benchmarks. So since you have a group, how can you assess because at some point you can have the real benchmarks, but you cannot use them for science.
Yeah.
Well, I mean, how confident are you that even if you notice some discrepancies between the real ones and the home-baked one that you can distribute, but on your side, you can still do the experiment on real benchmarks. So how confident can you be about the benchmarks so you can distribute so that people outside the area, because for instance, if I want to pay attention to this problem and to try some pseudo-Boolean encodings on them, well, will it be very different or not? So, I mean, what are the difference of behavior between your algorithms on real benchmarks and on those specific benchmarks?
Yeah. So what I can say is that a lot of the difference is that on the randomly generated benchmarks, the time is predominantly spent finding the solution, and proving it is optimal is very quick. Real world instances, it's almost the complete opposite. So there is a distinct difference. We have a forthcoming paper that actually exploits this to sort of point out, hey, look, we can solve basically all randomly generated instances very quickly because we exploit the fact that it's easy to find an optimal, it's easy to prove a solution is optimal. So we just heuristically look for one through relatively naive search methods, and then we can easily prove it's optimal. We also at that, like in this paper, and again, I wish the paper was out already, but it's hopefully soon. We are proposing a new set of random instances that are closer to the real world instances in a lot of these parameters like edge density, but a lot of other parameters as well. Unfortunately, due to the nature of kidney exchange programs, I guess, it's like, I spent months and could not find a good way of generating instances that would match across a number of parameters. It always felt like something was going wrong. So we have a better way of generating random instances, and I think they are a lot better. If you are interested in doing, especially if you're interested in doing experimentation sort of results on kidney exchange at the moment, I would highly recommend, I don't know how this is going to come across. I would highly recommend at least waiting a few months before sort of trying too much, just until we can get this paper out so we can give you some nicer benchmarks that would be a lot closer to the real world.
Okay. Thanks.
One thing that wasn't obvious to me with all these different constraints, but is it still true that we have in the end a 0-1 integer linear program, that it's enough to capture all of these different constraints?
So there, I think for almost all of the actual constraints, yes. There is, so I think the UK in particular has almost a peculiarity in their scoring function. And it's because we have to calculate the difference between the donor who is donating to a recipient and then the donor who is associated with the recipient who is getting that kidney. And because of that interaction, it does mean that we sometimes have to either adjust the model. So in particular, there's the PICEF model, which I mentioned was compact. We cannot use that in its compact setting for the UK system because we can't model this last fact correctly. But in general, yes, that is completely 0-1 binary.
And what you're saying also is that given the nationwide kidney programs today, I mean, solving the problems in 1 second sounds like you can do anything you want to do, but you can, like, if you would, but then you said if you try to scale it up to all of Europe, say, then you would actually not be able to solve it. Somewhere in between there, like you hit an exponential brick wall. Yes. Or what's?
Yeah. So even here in the UK, so we have the largest in the Europe in terms of size. We have 200 to 300 vertices in our graph. We call that. 200 we can do comfortably in under a minute. 300 is where it's sort of starting to get towards half hour. And I think 500 is basically at the point where the current software and algorithms that they are using will simply just not be able to solve it. I think they run into a memory issue, to be honest, but I don't know for sure. So it's definitely a point where at the moment, there is no sort of drastic need for new algorithms to keep existing national programs working. But if we are trying to develop some sort of collaborative approach that is going to involve at least more than 2 or 3 countries, then there is going to need to be some sort of improvement either in solver or in modeling techniques or pre-processing or something at least that can sort of get us over this current bump in the road.
Of course, you could also go to commercial MIP solvers, I guess.
Yes, that is also one option. I don't think, so again, the kidney exchange world is very much focused on looking at different models. Annoyingly, almost all of the scientific papers will compare and test various models using Garobi because it is free for academic use. And as far as I'm aware, all of the actual kidney exchange programs themselves will all use CoinOR. So I think CBC, I think.
Is it clear why?
I think, again, I think it's just because for the moment, at least, CBC is good enough for what they have. So even in the UK scheme, so that when I was saying sort of 200 to 300 recipients workable, that is 200 to 300 works with CBC. They don't even need Garobi for that yet. So it is possible that one solution could just be pay some money, get a license from Garobi to use Garobi or whatever, and that might be enough to solve the problem as well.
Would be less interesting from a scientific point of view, of course, but
yeah.
For all you know, okay, so it's not like like if I just take, you don't have data, like if I take exactly your model, your tricks, your diving, your whatever, and just swap out the solver and swap in another solver, what happens? You don't know.
There's not, I don't know of anyone who's looked at that sort of thing, no. And I think it is something that does need to be looked at more. Even between sort of CBC and Garobi or Cplex if it's still around, or whether it's comparing Garobi to some pseudo Boolean solvers or CP or something like that. There's not much of those comparisons. It feels like everyone just uses Garobi and assumes that that is the best that is out there.
Mm-hmm. I see. I don't know if we have any other questions.
Yeah, I mean, one of the things with Garobi is it has this 10 to the -6 magic parameter.
Yes.
So if you have really large weights on your objective function that are quite similar, I don't know if you still do this or whether you've replaced all this by hierarchical optimization.
I mean, I believe, so there's a couple of things. So the Garobi tends to be used for scientific articles, and I think people tend to not be as worried about those sorts of details in scientific articles, I guess. I don't know if anyone has dealt particularly with that, but at the same time, I want to mention that I don't think anyone does the hierarchical optimization in that manner. I think they do it actually as adding new constraint, forcing this to be this.
Yeah, I know in some of the other matching stuff, this was causing all sorts of problems.
Yeah, I've definitely had that issue with my own code when some people tried to test it on bigger problems, and I was like, oh yeah, here we'll add this bit in here, change the tolerance. There we go, solved.
Yeah.
So unless there are other questions, I think we end the official part of the seminar. So on behalf of everybody, I guess this is how you do it in the Zoom age. I guess I'll do my applauding, right?
Yeah,
and thank you so much for a wonderful seminar.
Yeah, not a problem. Thanks for showing up.